Science Max, experiments at large. Science Max! This episode is all about friction.
Yeah, friction!
Keeping things suspended up high thanks to friction, like this. And this. And even me.
Okay.
Climbing, sliding, lifting, and falling. Falling? I guess not yet. All on this episode of Science Max, Experiments at Large.
Greetings, Science Maximites. My name is Phil, and today we're talking about friction. I didn't slide.
Take two.
I can't, I'm still not. Oh, I know. I got it.
Take three.
Oh, socks don't work any better.
Take 15. 34. Take 36.
I don't know why I thought that would work.
Take 52.
I'm Phil, and today we're talking about friction! Sorry. Okay. Oh, friction! We did it! We got it, everybody! How many takes was that? Oh. Well, still, we got it. Good work. As you may have already guessed, today is about friction, and here's a really easy friction experiment you can do at home. All you need is a piece of wood. You don't need the frame, and you don't have to do anything fancy to it. Just put one end up on a couch or a coffee table and make a nice ramp. Then you want something to slide down that ramp, and I like to use a piece of wood. Now check it out. Wood ramp, wood block. The friction is so much that the wood slides to there. Now what I like to do is take a little flag and mark the results. Recording the results is good science. Now here's where it gets fun. Get another surface and attach it to the wood, like carpet and wood. Let's see how far this goes. Not as good. All right, record the results. Cardboard. Ooh, nicely done, cardboard. Foam. And this wood has been waxed, like on a floor wax, which makes it nice and slippery. Let's see how that does. Ooh. And now the ultimate ice attached to wood. This is actually harder to do than I thought. All right, let's try it out. Ice! The clear winner. Not a big surprise right there. And get this, once you've done all of that, you can change the surface of the ramp. You can go to waxed wood, carpet, foam, cardboard. But, well, yeah, you get the idea. Record all the results, compare them, and there you go. Friction ramp experiment. And that's what we're gonna be maxing out today. So come on, let's go. Check it out, I've improved the portal interface. Watch this. Yeah, and then I can scroll through experts, and oh, this is gonna be fun. And I've got my coordinates right there. Oh. That's never happened. Okay. Hey, Sarah!
Hey, good to see you again.
Good to see you too, Sarah. From Mad Science, you're gonna help me max out friction.
Yeah, friction.
What do you think of my max out friction room?
It's amazing. It's so wonderful. So how are we gonna max out friction today?
In the lab, I had a ramp, and I had stuff with different surfaces on it.
Oh, that's so cool. It's too bad you don't have it here. We could totally test that out.
I can bring it here.
Awesome.
I have a new app on my phone that talks to the portal, and let's see. That's not what I. Oh, hold on. Okay, there we go. And whoa. Well, I can do this. It needs an update.
Yeah.
That's what the. Yeah.
There we go.
It is. Okay.
Perfect.
So here we go.
Amazing.
The friction ramp, it's pretty simple. You just take, I've got blocks of wood with different surfaces.
Amazing.
And then you just slide them down the ramp.
Right. So cool.
Yeah, so what if, to max it out, what if this is us?
We're a block of wood?
No, I mean like we are on the block of wood, and then we can try changing the bottom. I guess a block of wood isn't the right thing to use, though.
Right, yeah. Maybe we could use like a sled.
Oh, yeah, okay, like a snow sled. That's a great idea. Okay, so we'll tell you what. I will portal in a sled for
Are you
us.
sure you want to portal it in?
I'm sure. Just
Okay.
stand back,
Okay.
though. Okay. Ha!
Ah, there we go.
Maxed out friction slide! You ready, Sarah?
Yeah, I'm ready.
Okay, here we go.
All right.
Sarah and I pushed each other around on the sled, which was fun, but it was also tiring.
It's pretty hard. This is my turn. My turn.
All right.
Oh, yeah! Whoa, friction! Yeah, friction! Yeah! Yeah, friction!
But we soon realized it'd be pretty hard to measure how much friction there was.
You know how hard you were pushing?
I had no idea how hard I was pushing.
A lot, but that doesn't really help in science terms. So
Exactly.
what do we do?
Well, with your first experiment, you used a ramp. Could we maybe put a ramp up in here?
In here?
In here, yeah.
I guess.
Then we can measure also how far we go so we know how much friction is being used.
Right, so we have our control, and then we have all the, just like the blocks.
Exactly, just like the block.
Okay, great. So we'll get the ramp, we'll get a bunch of wood,
Yes.
we'll get some tools.
Yeah.
The case of the missing friction! It was rough all over in the big city. My toughest case yet, and I felt like I was getting nowhere. Someone stole all the city's friction. And it was my job to find out who and get it back. But after a week, I was no closer to solving the case. It was hard to get anything done now that there was no friction. Uptown to downtown, people were sliding all over with no way to stop themselves. It was chaos. Chaos, I tell you. But if there was any detective that could solve the case, it was me. But it's like my grandma always said, it's tough to follow leads if you can't sit in your chair. Nothing stays put in a city without friction. And you never appreciate something till it's gone. The phone rang. Sure, I wanted to answer it, but it slipped through my grasp just like this case. The mayor was on the line. He wanted to know if I'd made any progress. But I felt I was going in circles.
I'm gonna have to call you back, Mr. Mayor.
Without friction, you couldn't do very much at all. It was going to be my toughest case yet.
Sounds good.
Sarah and I are maxing out a friction ramp. Step 1, make a giant ramp.
There, are we done?
Great, I think so.
We're done. But it proved a bit hard to lift up to the second floor. Fortunately, Sarah had an idea.
Maybe we could use this crane.
We use the crane! Oh, yeah, I've got a 5-ton crane at Science Max headquarters. Good thinking, Sarah.
So we rigged it up and tried it out. The bonus was we could make the ramp any angle we wanted.
Okay, time to get my helmet, because don't go any higher than that, because I don't have my helmet. And then we will start sliding down.
All
Friction
right,
ramp!
friction.
I got on the slide and Sarah lifted it up until I started moving.
Ah! Friction ramp!
And that allowed us to record our results.
We're at 2 meters.
2 meters!
meters.
Recorded. First recording done,
All
now we
right.
switch it up.
We tried it again with Sarah on the slide to see if she slid at the same height. And she did.
Yeah.
Now we have a way to record the results. The plastic sled went down the ramp at this height. Things with more friction will mean the mark is higher, and less friction will mean the mark is lower. So then, we tried it with...
Cardboard! Cardboard! What did we get?
And it was...
A little over 2 meters.
meaning...
Cardboard is a little bit less slippy than the plastic of the sled.
All right.
Ready for carpet sled?
Good to go.
Here we go. Oh, past 2 meters. Oh, almost 3.
Here we go.
Carpet had even more.
Oh my gosh, we're going to the side. That
Whoa!
was so cool.
That was exactly 3.
Then we tried... foam!
Coming up on 2 meters. All right, coming up to 3.
And just like the wood block, the foam didn't slide at all.
What if I like do this and then I slide? Right, so, friction sled on foam, highest friction of all of the materials. Oh, hello there. Here's a fun science experiment you can do with science and friction together. Take two books, put them on top of each other, and pull them apart. Ooh, not too much friction. But if you take the books and you interleave some of the pages, maybe 3 or 4 parts, and try it again, pull them apart, they're a little harder to pull apart. That's because the friction for more pages touching each other actually starts to add up. So, what if we were to take 2 books with a lot of pages and very carefully and meticulously take each page individually, one at a time, and overlay each one and go back and forth? These are 2 books completely shuffled together. The elastic band is actually just to hold the covers together. All right. So, now the friction between all of these pages, when I try to pull it apart, makes it pretty much impossible. Now, there's 2 things going on here. First of all, when you start to pull the books apart, the pages start to stick together because they squeeze together, because you're pulling and they're squeezing. And the fact that there's so many pages sticking together, the friction builds up to a degree that is actually very impressive. But don't take my word for it, let's max it out. Here is another 2 books, elastic just to hold the covers. This one clamped to the wall, and I'm gonna pull on this one. Science! Still don't believe me? Well, let's max it out some more. 2 books, all the pages layered together, held together only by friction suspended over a giant vat of slime. Now, let's see how much faith I have in science. Friction! Yeah! Okay. Okay, oh no. Okay, now to get down. Okay, hold on. And then. Science! That was close.
Sarah and I have used our maxed out friction ramp and compared the regular sled to cardboard and foam. What's next?
We've waxed the bottom of this sled, and we're gonna try a wax sled next.
Wax sled!
All right, here we go. All right.
1 meter.
Oh, boy.
1.5 meters.
Whoa!
Wax sled! Woo!
Whoa.
The slipperiest yet, only
Yeah.
1.5 meters.
That's awesome. Do we have anything that's more slippery?
Yeah, we do. We have ice sled. Are you ready to try it out?
So ready to try it out.
Okay, let's do it.
All right.
And
There we go. Whoa! That was awesome.
look how far you went.
That was so cool.
And only 1.25 meters.
Least amount of friction.
Ice wins. So, I think we should do something else to max this out, though.
Maybe bringing it up a little bit more and
Yeah.
using something with less friction.
Wait, I have an idea. Yeah, okay, come with me. This is a climbing frog. Why does it climb? Because of science. I pull on this rope, and then I pull on that rope, and I pull on that rope, and he climbs up the ropes. And why? Well, because of friction. The secret is 2 straws.
The straws are pointed away from each other at the bottom. This allows it to climb thanks to friction. Take a closer look. When I pull on one string, it pulls straight, which makes the frog pivot. That string slips through the straw because there's not a lot of friction, but there's lots of friction on the other side because of the angle. So one side of the string goes down, which makes the other go up, which means the frog goes up with it. All thanks to friction.
So now, let's max it out. This is a super maxed out climbing frog.
Just like the small version, I have a rope going through 2 tubes. I pull on one rope and the other holds on by friction. Then I switch.
And it does work. It's just a lot harder to pull on the ropes, but it totally works. Whoa, guess what? There, and then this one, and then that one, and then that one. Yeah! A giant climbing frog! All because of friction. Here's another way to defy gravity using friction. Get a plastic water bottle and fill it with rice.
Take 2.
So get a plastic water bottle and fill it with rice using a funnel. Then take a shish kebab skewer and stick it into the bottle and nothing happens. But if you tap the bottle down, the rice starts to pack in a little bit better. See how the level of rice is lower? Which means you can add more rice. Pack it down even more. And you can even use something the same diameter as the mouth of the bottle, like, say, a highlighter. And make sure all the rice is as packed in as you can get it. There. Now the rice is really packed in there. And when I stick the shish kebab skewer in, the friction between the pieces of rice and this wood is enough to lift the bottle using nothing but friction. Now, let's max it out. I filled this 20-liter water cooler jug full of rice, and it's really heavy. I wanted to see if I could lift it using nothing but friction and this dowel, which is just a round piece of wood. All right, here we go. Ah, science! I'd max it out even more, but I don't think I could lift anymore. It's okay, I could just fit.
Newton's first law in 60 seconds.
Newton's first law says an object in motion tends to stay in motion. So why don't they? See, if I was to throw this, it doesn't stay in motion, it doesn't keep going, it slows down and falls to the ground. Well, the whole law states an object in motion tends to stay in motion until an external force acts upon it. So what forces are acting upon this? Well, gravity for one, pulling it down towards the ground, and friction, specifically air friction, slowing this down and making it stop. Now, if you were to have something very light with a lot of surface area, it would really be affected by air friction. You wouldn't be able to throw it very far at all, no matter how hard you tried. So there you go. Newton's first law, an object in motion tends to stay in motion unless it's affected by an external force, such as friction, like air friction. So there you go.
Sarah and I have recorded a lot of results on our ramp by raising it till we started to slide.
Here we go.
Now we've decided to raise the ramp to the highest point and see how far we can go using some low friction things, like a wheeled cart.
I've made a double bike cart.
Wheels are great for moving. They have rolling friction,
Ready?
which is different from sliding friction.
What happened?
You went through all those boxes back there.
That was it. We went really far. Total fun. Let's try something else.
So what are we gonna do next?
Now we're gonna do the frictionless thing that we have at Science Max headquarters, a hover disc.
Oh my gosh, that's so cool. Where did you get it?
Built it, season 1.
Amazing.
As you may remember from that episode, a hover disc uses air to greatly reduce the friction with the ground.
Here we go.
So what would a hover disc do on a ramp?
Right.
Only one way to find out.
Whoa! That was amazing.
That was awesome.
So let's recap. Friction is when two surfaces rub against each other. You can have a very small amount of friction or a very large amount, depending on the materials. And using science to reduce friction results in the best sledding experiences.
Nicely done. Science Max, experiments at large. Your turn?
My turn? Yeah, let's do
Okay,
it.
so take those, and I'll get this, and then I'll give you the helmet. And then we gotta rebuilding the boxes is like the hardest part of this
Yeah.
whole situation. But
We're getting slightly wet on this episode of Science Max. We're looking at propulsion, how to make things move.
initial thrust, constant thrust.
And those things are boats. Boats. Okay, one skateboard and two bikes, but mostly boats. On this episode of Science Max, experiments at large.
Greetings, Science Maximites. My name is Phil, and today on Science Max Experiments at Large, we are using mouse traps, but I cannot find my mouse traps, so it's gonna be a little hard to do the experiment unless I have... Oh, hey, here they are. Oh yeah, I stored them preset. Why would I do that? Okay, well that's fine. Anyway, today we, careful, are going to be using mouse traps. Like I said, we are going to be using mouse traps. Mouse traps as a form of propulsion. That's the force that makes things go, and we are going to be making a boat go. And what is the thing that's going to make this boat go? A mouse. Oh, it's not set. Sorry, I'm really jumpy. Anyway, we're gonna be using a mouse trap. And don't worry, no mice are gonna be harmed in the making of this or any Science Max episode, but mouse traps are really great because they can store energy in the spring. If you see, there's a spring that makes this bar want to snap back, but we can put energy into the spring and store it and then use that energy as it unwinds the spring to propel our boat. But it's a little more complicated than just this, so come on, I'll show you. What we're gonna do is build this. This is the mousetrap boat, and it works like this. I've got the mousetrap, and it's attached to a long arm. That arm has a string on it, and it goes around the paddle wheel, and as the mousetrap unwinds, the paddle wheel spins like that, which pushes the boat forward. Now, it looks kind of complicated, but it's actually quite simple to make, and here's what you need.
My mousetrap boat is made with styrofoam, craft sticks, and elastics. You'll also want a pencil, plastic drink caps, a shish kebab skewer, small zip ties, string, and of course your mousetrap. Now, mousetraps can hurt your fingers, so get an adult to help you when you use them. Start with 2 pieces of styrofoam. I like to cut mine into this shape, but the only really important thing is that they're the same size. Your paddle wheel is made from a circle of styrofoam with it penciled through the middle, and it will go across like this. To make the paddle wheel, I use cut pieces of craft stick.
Or they can be plastic, and make some cuts and then put them in like this, and that is what will make your paddles on the paddle wheel, because that's the wheel and that's the paddle wheel. That's why they call it that.
Stick drink caps to the ends of the pencil after sticking it through the styrofoam. I like to use a few craft sticks and elastics to help give the styrofoam strength. Next is the mousetrap, which you want to glue down to a frame of 4 craft sticks. Attach the frame to the boat with elastics, then attach the shish kebab skewer or a pencil to the mousetrap with zip ties. I like to put some craft sticks on the end to make it easier to tie the string to it. Wrap the other end around the paddle wheel pencil, and remember you need enough string so that your stick can lie flat.
Okay, let's try it out.
Wind up the paddle wheel. This'll be a little hard as the spring will pull back, but that's where you're storing the energy. And when it's wound up, put it in the water and
Let it go. The paddle wheel turns because the mousetrap is transferring energy that we put in earlier, and it goes all the way.
we stored the energy in the tension of the spring. Now that tension is pulling the mousetrap, the stick, and the string, which turns the paddle wheel and makes the boat go.
Mousetrap-powered boat!
If you want more detailed instructions or other designs, look up Mousetrap Boat.
And there you have it, the mousetrap-powered paddle wheel boat. And this is what we're going to max out today. Come on. All right, time to pick an expert and go off to max it out. Careful. Okay, let's see here. And, who to pick? Michaela from the Ontario Science Center. She'd be perfect. All right. I ended up in the water again. Oh well, at least maybe Michaela made it. Oh, Michaela!
Whoa, Phil!
Are you okay?
Are we still fixing the portal?
Yeah, I needed to tweak it just a little bit. It's a little off again. Anyway, great to see you, Michaela from the Ontario Science Center. You're gonna help me max out the mousetrap boat.
Awesome.
Yeah.
Wait, where's the boat?
I don't have it. I thought it was gonna come through the portal. It could be anywhere, really. I mean, it just... What? Oh, here it is. Okay, good. So here is the mousetrap boat. Check it out. So got a mousetrap here, right? And you wind up the paddle wheel, and it goes. Yeah, right on.
Awesome.
So what do you think we should do in order to max this out?
Well, first idea, I'm just thinking more mouse traps.
More mousetraps. So we just make a boat and it has like 10 mousetraps on it.
At least.
Okay, great. Actually, I had mousetraps coming through the portal as well.
Okay.
Oh. Okay, we're all right. Okay, so now we've got the mousetraps. We can start building. Let's collect them carefully, though. I don't know if they're... Initial thrust or constant thrust. What's the difference? It's all about power. Uh-oh. Paper airplane initial thrust. It gets all of its thrust from my throw. Initial thrust. If you want constant thrust, you have to take the thrust with you, like this. There's a lot of cats in here. Initial thrust. Initial thrust. Initial thrust. All the energy is put into the beginning of the... All the energy is put into the beginning. If you want constant thrust, then the thing has to produce power while it's moving. Wind up car, constant thrust. Actual car? Yeah, that's constant thrust because you have an engine. Of course, not this car. This is a toy car. But you know what I mean. Check out this fishing rod, and on it I have a lure with a hook. Now watch this. I cast it out, initial thrust, but then I use the reel and start winding it back in. Constant thrust, huh? Two thrusts in one. And now you know the difference between initial thrust and constant thrust. Hey, I caught a fish. Hey. Oh, easy, kitty. Nice kitties. Easy, Ramona!
Michaela and I are maxing out a mousetrap boat. We built a larger version with 10 mousetraps all in a line.
So it looks pretty good. I think we're ready, right?
Yeah, I think so.
Got a whole bunch of mousetraps. Should we wind it up and see
All right.
what happens?
Let's do it.
I think this is gonna go pretty well. What do you think of that stick? Is that gonna bend too much? Is that gonna snap or?
Looks pretty flexible.
I mean,
I think we're okay.
I think we just keep going until it breaks. Ooh. Now it's starting to look very fast.
man.
Yeah, like it looks like a speedboat. Okay, ready? Go. Well, positive. It is working.
It's not gonna win any speedboat
It
races.
is not going to win any races at all. But it's totally working. The mousetraps, they're pulling on the string. The string is making the paddle wheel turn. Just not much. I would have thought this many mousetraps would be a little bit more effective.
Yeah, it looks like we're going for distance over power things. See,
Oh,
we're
right,
using
because-
a lever here. That's a lot of distance for this to travel. But if
Small
we
amount of force over a much longer distance, that's how a lever works.
Exactly.
So we slide the rope down further on the stick, then we would get more force, and it just wouldn't go as long. Okay, so why don't we try that? Wrapping, like that.
Nice.
All right, once again.
Trial 2.
Okay,
Okay.
ready?
Ready, set.
Go! Ah!
Hey, that looked better than last. Oh, now it's picking up.
Yeah, that's really working. Whoa, careful. Oh, look out! Look out! So, good. It's good.
Hey.
It's not great. Not yet.
Yeah,
Right? How do we make it better? What do you think?
Well, I was thinking, what if we try to reduce the friction? Remember that other boat we tried
try?
Here it is.
Oh, yeah.
The little one, you mean?
Yeah, the little one. See, look at this one. It has a pontoon style. Do you see how we have it floating on these two surfaces?
Yeah.
So very little is actually touching the water. Whereas
Oh.
this one, we have a giant hull that's going to drag the water and slow our boat down.
So it's sort of like the difference between like pushing a whole bunch of water like that and pushing the water like that.
Yeah, we want very little resistance for our boat.
So little resistance with a couple things that just stick down like that. A lot of resistance when we have big, flat, big, like that. So we completely rebuilt this boat. Shall we do it?
Yeah, let's do it.
Our jewels floated away again.
Oh.
Race ya! Our maxed out mousetrap boat isn't the only way to give a boat propulsion. Let's look at another way using a balloon. Let's make a balloon-powered boat. All you need for that is something to be your boat and a balloon. Then you attach them together. Actually, the best way to do it is use a straw and attach the balloon to the straw using an elastic band. And then you attach it to your boat using more elastic bands, just like this. I've put a nice tape top on the boat to make it look awesome. And I also put a little bit of a riser here using just anything plastic to keep the straw nice and straight, because the question is, will our balloon-powered boat work better if it's pushing in the air or if it's pushing in the water? Well, let's do a science experiment and find out. First version, in the air. Oh, almost all the way. Now let's try it with the straw like this so it pushes into the water. Whoa, works so much better. Why? Because water is denser than air.
The air coming out of the straw has to push against something to make the boat move. Water has more mass than air, so pushing against water has a better result.
Now, let's max it out. This is an air compressor. Well, actually, that is the air compressor. You see, the engine here pushes air into this tank, which works sort of like the balloon. And then it goes out this long hose, which sort of works like a straw. So let's make a maxed out air-powered boat. Ready?
Just like the small boat, pushing against the air doesn't produce much thrust.
Huh. Not so great. But now let's put it in the water.
Pushing against the water gives me much more thrust because water is more dense than air.
Oh. Maxed out air-powered boat! Maxed out air-powered boat! Yeah! Whoa! That's not me.
Michaela and I are maxing out the mousetrap boat. 10 mousetraps didn't seem to make our boat go very fast. But moving the string down our lever arm helped, and now we want to redesign the hull so it has less friction with the water.
Check it out. This is the ultimate mousetrap boat. We got 10 mousetraps here. We got our long arm. We have it attached at the right point of the lever, we think. And then we've got two paddle wheels at the back and pontoons.
Yes.
Yeah, so what do you think, Michaela?
This thing is set.
It's gonna be awesome?
Yep.
Okay, ready?
Ready? Let's test it.
Whoa, it's working.
Hey,
It's working.
Picking up speed.
Yes.
Wow.
Whoa, mousetrap boat. I mean, it's good. It's good. It's not Science Max good.
Yeah. We were hoping it would go faster.
Faster
No.
or? No, pretty much just faster. Yeah, okay. Obviously, we need to store more energy. That will make the paddle wheels go faster, right?
Yeah, so we just have to think about it, right? Like, what's stronger than a mousetrap?
Well, 10 mousetraps. That's why we have 10 mousetraps, Michaela.
Okay, what's stronger than 10 mousetraps?
11 mousetraps? Like, if we just keep going and
Okay,
it's just
enough
gonna
with
get
the
super
mousetraps.
wide, we have 1,000 mousetrap wide. What?
Enough with the mousetraps. Have you ever seen, like, a rat trap?
No?
They're huge.
Well, hold on. I can just get one from the portal. One rat trap coming up. Oh. Okay, Kim. All right, well, that's fine. And whoa!
Wow!
Yeah,
look at
that is a lot bigger. Okay,
Huge
so snap
difference.
yours.
All right,
Is it?
ready? Mousetrap.
Okay.
Okay.
That's terrifying. So that's a lot more power.
Yeah, a lot of force.
So tell you what, we have a little mousetrap boat. Why don't we build a little single rat trap powered boat and we'll race them. and we'll just see the difference in power from one rat trap and one mouse trap.
I like that. We'll do a prototype before we make a big one.
Yeah, okay, come on, let's go.
So we built a rat trap boat to race the mousetrap boat. And then Michaela and I got a little competitive.
Check out the rat trap boat.
No, check out the mousetrap boat. Mousetrap boat is better because...
Yeah, rat trap boat is better. It's got bigger springs, more potential energy stored in here.
And mousetrap boat has less potential energy and less springs, but he's got more heart, and he really wants to win.
Hey, yeah, I'll tell you what, Phil. Loser jumps in the pool.
What? Oh, okay, sure, let's do it. Okay, ready? Go!
So, as you may have guessed, the rat trap boat has a lot more potential energy that can be stored in the spring.
Okay, so rat trap boat is clearly better than the mousetrap boat. We make the boat the same way,
Yeah.
but we use rat traps instead of mouse traps. What do you say?
Love it.
Okay, let's do it.
Let's do it.
Yeah.
Wait a second, Phil.
What?
Fair's fair. You gotta jump in the pool.
Okay, fine. Here you go. Hold this. Inertia. What is it? Well, it's directly related to Newton's first law of motion. An object in motion tends to stay in motion, an object at rest tends to stay at rest. Let's do an experiment. Here is an object. Right now, it's at rest. You might think that means it has no inertia, but that's not true. Inertia just means an object's tendency to keep doing what it is doing. Right now, it's doing nothing. But if I wanted to overcome its inertia, I would have to put energy in. And now that I have, it is moving on its own. It has inertia. If I wanted to stop it, I would have to overcome its inertia, its tendency to keep moving. There. I went exactly that far. Now, let's max it out. I'm adding these weights to the cart. Now it has a lot more mass, which means it has a lot more inertia and its tendency to do nothing. But this time it has a lot more inertia. If I wanted to get it going the same speed as before, I'd have to put in a lot more effort. There, now it's going the same speed as before, but now it has way more inertia, so stopping it will be harder. So there you go, inertia. Things' tendency to stay moving or stay still, and the more mass, the more inertia. Dear Phil, I can't believe you did a whole episode on boat propulsion and you didn't use the greatest thing out there for making a boat move, a propeller. Sincerely, a fan. Well, let's talk about propellers. Oh, good thing this is fan mail. Get it? Because it's a fan? Yeah, anyway. A fan pushes air just like a boat propeller pushes water. They're both fluids and they behave in the same way. Now, if you look closely at a fan, it's curved on the blades. The air or water is caught under at this side and then it's pushed out on the curve to make it go that way. And the faster it spins, the better it works. Now, this is a propeller-powered boat. And what you do is wind up the propeller. I have an elastic band here to store the amount of energy I put in. And then you put it in the water, the propeller spins, and the boat goes forwards. It's being propelled by the propeller. That's why you call it that. Awesome, right? Well, now we'll max it out. This is a drill. It spins. And this is a propeller, and when you put it in the water and spin it, it provides thrust. So let's try it out. Whoa!
Remember not to try this at home. I am a trained professional.
This is a very small propeller. Let's compare. This is a super maxed out propeller. Whoa, okay, let's try it out. Whoa!
The larger a propeller is, the more energy you need to turn it, and the more propulsion you get out. Michaela and I are maxing out the mousetrap boat. Well, actually, we can't call it a mousetrap boat anymore because now we're using rat traps. The design is the same as our 10 mousetrap boat.
Rat trap boat! Rat trap boat! It's the super most rat trap boat ever!
We wind it up and try it out.
Okay, ready? Go!
It worked great. The reason is because this boat was storing a lot more energy in the spring tension. More energy means more propulsion. So much we couldn't even catch it.
Yeah! Rat trap boat! Science Max, experiments at large, rat trap boat, high five. Let's do it again.
We're flying again on Science Max.
Gliding squirrel.
Throwing things, spinning things, tumbling things, and maxing things out just a little too much.
Go, go, go! Go, go, wait.
Keeping things up in the air is what's on the runway for this episode of Science Max, Experiments at Large.
Well, hello there, Science Maximites. Today, we are going to be flying on Science Max Experiments at Large. Take a look at this. It's my paper airplane. Give her a bit of a throw and she flies amazing. Now, take a look at this. This one is lighter than air. It's a helium balloon, and guess what? It flies on its own. See you later. Well, just hold on a second there, friend. What's this whatchamacallit called? I'll tell you. It's called a hoop glider. Give it a toss and she flies really well. But today we're flying in a whole new way, Science Maximites. I know it sounds like we've covered all the bases for flying, but we haven't. Come on, follow me. Oh, didn't actually realize how much these goggles would fog up. Where was I? Oh, right, we're flying today on Science Max. Come on. Today, we're going to be building a tumblewing. That's a kind of paper airplane that flies on a cushion of air. This is a big mouth tumblewing. It doesn't look like much because, well, it's not. It's just 2 strips of paper taped at either end. But what you do is you throw it in the air and you walk along behind it with a hard surface like this, and that little scoop of air keeps it flying. And here's how you can make a tumblewing of your own. But first, a word about paper. Did you know that paper comes in different weights? The kind of paper you get from the printer is actually pretty heavy. The ideal paper to use for tumblewing making is from a phone book. You may not have a phone book at home. They're kind of rare right now, but its paper is very, very thin and the perfect for tumblewing flying. Now, if you don't have a phone book around, you can use newspaper. It works almost as well. What you do is you cut out some strips of paper, and you just need 2, and you put them on top of each other, and then you offset them, which means you take the top one and you slide it over till there's about maybe a centimeter, 2 centimeters, something like that. And then you take your handy dandy science tape, which is the same as regular tape, except you use this tape only for science, and you tape the edges very carefully like that, and flip it over to the other side. Make a little tape on this side, just like that, and there you go. You have a big mouth tumblewing. Now you also want to tweak it just like you do with a paper airplane. You want to curl the paper a little bit, curl this side a little bit, and let's see how it flies. You'll know you have it right when it doesn't go to the left or right, but just opens up and tumbles straight down. Ah, not too bad. That one curved a little bit, so I'll have to tweak it a little more. Now, the other thing you're gonna need is a nice hard surface. The kind of signs that you get when there's an election are perfect. I happen to have a few of these sitting around, and they are made of something called corrugated plastic. They're very light, but they're also very hard. So you can use this, but you can also use cardboard if you don't have any of these around. So what you wanna do is get your tumblewing and your hard surface and flip it in the air, get it flying very nicely, and then walk behind it with your board, and a scoop of air will be behind it, and it will fly. But it may look easy when I do it, but that's because I've been practicing quite a bit. So here are some tips for tumblewing flying.
Tumblewing flying tips. When flying your tumblewing, you want to be indoors, away from any wind or other kinds of moving air. A long hallway or a big room is best so you don't run out of space. The angle you hold your board is important. Too much tilt or too little and it won't work. Keeping your tumblewing in the air is mostly about the speed that you walk. Too fast and the tumblewing will go over the top. Too slow and it'll fall. Finally, practice, practice, practice. Happy tumblewing flying!
Now I just need an expert to help me. Okay, let's see here. Lisa from Logic's Academy. She'd be perfect. Okay. And, oh wait, I need a lab coat. Oh, and Lisa needs a lab coat. There we go, Lisa's lab coat. Good, my lab coat. All right, my turn. Oh, my lab coat changed color again. I'll fix it later. Lisa's gonna be here any minute.
Oh,
Hey!
that was so fun!
Oh, did you like the portal?
I loved it. Hi, Phil.
Lisa from Logic's Academy, I'm glad you're here. Your lab coat changed color as well, though. It's supposed to be yellow. I think we had a glitch.
I kind of like it though, blue.
No, but we gotta do yellow. Yellow is the Science Max lab coat color.
Okay.
So, we are here to talk about the tumblewing. I've got my big mouth tumblewing here.
I have
Got
mine
yours?
too. Yeah.
Now, what are we want to max it out, obviously. What else can we do?
Well, actually, there's a lot of different designs that we could try. This is a big mouth tumblewing. There's also tumblewings that are just a straight sort of single wing.
Oh.
And then there's some that are like an actual airplane or a glider.
Ooh, and we can max them all out.
Of course.
All right, let's get started.
Let's do it.
And we'll get the yellow lab coats.
And I really like the blue.
We gotta get the yellow on. There, now we've got our yellow lab coats. I've got my big mouth tumblewing, and I got my board to push the air.
Oh, look at that! I voted for you.
You did?
I did.
Oh, you were the one. Okay, so let's talk about the science going on behind this air surfer.
Okay, so just like in an ocean, if you were surfing in an ocean, you'd be surfing on a wave of water. Right now, our tumblewing is surfing on a wave of air that you're creating with a board. And air and water are actually both fluids.
Oh, cool. So we
They
can.
behave the same way.
So it really is surfing.
It is surfing. And actually, sometimes we call those air surfers.
Cool. Well, why don't we have a surfing competition? Because I actually have here a Team Phil board and a Team Lisa board. Okay. So what do you want? You want to have a race?
Yeah, absolutely.
Okay. You want to take this one? This one flies really well.
Definitely.
I'll make a new one.
Okay.
Welcome to the Air Surfing World Finals, almost live from Science Max headquarters. I'm Jim and I'm joined by Chuck. Today it's Team Phil versus Team Lisa.
Team Lisa has a lot of heart, Jim.
But Team Phil is on his home turf. Let's see how they do. Round one is, of course, the tumblewing race.
And a great day for air surfing. The teams are ready, and there they go.
Ooh, Team Lisa looks like she had some trouble starting. Team Phil has already pulled ahead, but Team Lisa is off the marks now.
I think that beginning fumble might have cost her.
Let's see. Team Phil with a commanding lead, but Team Lisa's catching up. Oh, Team Phil loses his tumblewing at the last minute. A great dodge and a pass by Team Lisa. Can she hold it? And no!
Taking 10 steps back is the rule when you drop your tumblewing, Jim. It's anybody's game.
Looks like Team Lisa fumbles her start. Phil pulls ahead. Can he be caught?
Almost at the finish.
Yes. Team Phil with the win. What an upset.
All right, you had a lot of practice with that one.
Yeah. Okay. So you got another design?
Yeah, let's try the single wing
New
one.
design.
So at the end of the first round, we have Team Phil with 1 point, Team Lisa with 0.
But now we go to the second round where the design changes. We're now looking at a single wing design. It still tumbles like the big mouth tumblewing, but made from a single wing.
Does that make them harder or easier to fly, Chuck?
A bit harder. They're faster and more maneuverable.
If you wanted to, you could research tumblewing, and you would be able to find this design. And this is what these show you where to fold it.
Yes. So the dotted lines or the dashed lines are where you would fold, and the solid lines is where you would cut.
What's more, Team Lisa has more practice with this version.
And they're off. Oh, Team Phil with another early lead, but Team Lisa's catching up.
Phil doesn't have much practice with this version, and it's starting to show.
You're right, Phil fumbles. Oh, Phil fumbles, and Lisa passes him for the win. There we go. At the break, we're all tied up with Team Phil and Team Lisa with 1 point each.
Look how well mine's going. This is an ornithopter. It's a machine that flies by flapping its wings. When people were still trying to figure out how to get something to fly, they thought, copy a bird. A bird flaps its wings, and it flies, just like this. So, why don't we have airplanes that fly by flapping their wings? it turns out that flapping wings is actually complicated mechanically. First of all, you have to tilt the wing when you go up so it doesn't take as much air, and then turn it so you push more air on the downstroke. So flying like this would be kind of hard for an airplane and really hard to do on a large scale. So humans came up with this, our propeller. Our propeller catches the air, and if you spin it fast enough, it gives you lift. So if you orient it upwards like a helicopter, it will give you lift, or if you orient it this way, it will give you thrust, just like an airplane. So that begs the question, why don't birds and insects use propellers to fly? Turns out, though, that rotating a propeller is really hard to do with something that has muscles and tendons. So in the end, birds fly by flapping their wings, and humans first learned to fly by rotating a propeller. Science.
Lisa and I are air surfing. We've tried 2 different versions of tumble wings, but now Lisa has a new design, one that doesn't spin as it flies.
Okay, so what do you have now?
Oh, check this out, Phil. This is a mosquito glider.
All right, so it's like a paper airplane.
Yeah, but it's not made of paper. It's made of a light foam.
Ooh.
The mosquito gliders work the same way as the tumble wings, but because they're much larger, they're much harder to control.
I got it. Oh, no, 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 no. Oh, almost into the stuff. Not bad, though, right?
You got it.
This is very tiring.
This is really hard. It takes a lot of flying time to master.
We got the hang of it, but we quickly learned that you have to run a lot faster with the gliders. And we were soon out of breath.
Whoa, sorry. You gotta be in good shape for this.
Turns out a bigger glider is much harder to fly. So,
Ultra maxed out mosquito glider.
we made it even bigger. Why? Well, because it's Science Max.
Bigger board.
We needed a much larger board and tried first with 2 people.
Ready? Going. Oh.
And then with 1. And the most we were able to get it to fly was... not a lot. Our conclusion?
Large airplanes just don't fly very well.
Well, homemade ones.
But we can try something else.
Okay,
Let's try something else.
let's try something else.
Today only, I got a super special on anything that can fly. Go on, pick something out. Oh, you had the paper airplane. Oh, good choice. Good choice. But guess what? Paper airplanes don't fly. Full price. Yeah, I know, but before you start arguing with me, you need to know the difference between flying and gliding. A paper airplane does not fly, it glides. You need constant thrust in order to fly. If you do not have constant thrust, then you glide. Take this bird. This bird can fly because it flaps its wings. It has constant thrust. On sale. But this airplane cannot fly. You give it some initial thrust when you throw it, but after that, it can only glide. Full price. But look at this. It's an airplane powered by a propeller on an elastic. Now we're talking constant thrust. It can fly. On sale. But it can get confusing. I mean, look at this flying fish. Nope. Flying fish cannot fly. They can only glide. Full price. Look at this. It's a cute little flying squirrel. He climbs a tree, jumps off from a high branch, opens his legs, and there's a little flap of skin there that allows him to sail to another tree. Haha, flying squirrel. No, not flying, no constant thrust. Gliding squirrel. Full price. Okay, tell you what, you came all the way down here, I'll make you a deal. Check this out. Flying fish, now it has a propeller, it has constant thrust. It flies for real. And ditto, squirrel with a jet engine. And now you know the difference. Something that flies has to have constant thrust. Otherwise, you're just gliding. Squirrel away! I forgot to gas him up. Look at those clouds. Aren't they nice? Did you know there are different names for clouds? Like those clouds right there? Those are cumulus clouds. They're the kinds that look like cotton balls, really fluffy and light. Well, they're not exactly fluffy and light. First of all, they're not fluffy, they're wet. It would be sort of like being a very dense fog, and it'd be very wet if you were in that cloud. And they're also not light. In fact, they're not light at all. That cloud right there weighs about 500,000 kilograms. That's the same as 100 elephants. 100 elephants just floating around in the sky? Come on, how does it do that? It does that because it's so spread out. But water is very heavy. Interesting to think about. 100 elephants just floating around in the sky above our heads at all times. Almost makes you want to go inside.
Our air surfing tumblewings worked well, but our mosquito gliders were a bit too maxed out to fly really well.
Large airplanes just don't fly very well.
Well, homemade ones.
But maybe we should try maxing out the tumblewing just to see what happens. So we did!
Okay, Lisa, I'm gonna throw it, and then you're gonna push the sign.
What?
Go!
Ah!
Wait.
Oh, did it go? What happened?
It didn't, whoa, it didn't work.
We tried it, and and it turns out, yeah, it doesn't fly.
Go, 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 go! Go, go, wait.
But I mean, this is Science Max, so of course we had to at least try maxing it out.
Phil,
I don't know if this is working.
it's heavy.
It's very heavy. Okay, maybe we should go back to a slightly smaller version.
Sounds like a plan.
Okay.
High five?
High five. This is a boomerang. Boomerangs are from Australia, and the cool thing about boomerangs is when you throw them, they come back. With practice. That was close. When you throw them, they come back. And it comes back. Comes back. Come back. Come back. So, why does it come back?
Well, if you take a look, it's made of two wings, like airplane wings, but with one important difference. You see, a wing has a shape called an airfoil, and this gives lift. But check it out. The boomerang has one airfoil pointed this way and the other pointed the other way, which means if you spin it in the right direction, each wing will get lift as it rotates. But how does lift make it come back? Well, that's the trick. You see, you throw it sideways. The lift from the wings makes it go in a big circle and come back to you.
So when you throw a boomerang, this side starts to go this way and it gets a little bit of lift. Then this side gets a little bit more lift, and then this side gets lift, and each time it gets lift, it starts to turn just slightly. So as the boomerang spins, it describes a nice big arc in the sky and comes right back to you. Ha-ha! And that's how a boomerang works. Thanks, Phil. No problem, Phil. Hey, do you want to get lunch? Yeah, lunch sounds good. Okay, come on. Well, the Science Max headquarters has a nice cafeteria.
We've tried air surfers of all shapes and sizes. And what have we learned?
Maxing out an air surfer by making it bigger is really difficult.
Very difficult, yeah.
So what we've decided to do is go back to our original big mouth tumblewing and instead do it on a maxed out obstacle course!
Tumbling surfing round 3, the maxed out obstacle course. Let's take a look at the obstacles. The tree slalom, the podium ramp, the hanging hoop, ring walk, wall of boxes, ladder tunnel, side hoop, ball promenade, and the barrel run.
So here's how we play. I go through and then you follow me. And if you make it through an obstacle and your tumblewing's still in the air, you get a point. And at the end, we count how many points we have and we see who won.
And it looks like they're ready to start. Here we go!
Where are you, Team Lisa? Oh. Oh, yeah. Oh, no. Okay, what do I do with the boxes? What do I do with the boxes? Going through the boxes! Definitely didn't make that one. Recover! Oh, oh, oh. Oh, oh. Okay, definitely lost a point there.
I'm almost there! Right behind you!
Oh, yeah! Uh-oh, uh-oh, uh-oh. Knock the barrels over, getting
I
through
get
the
an
finish
extra
line.
point for
And Team Lisa. Oh, yeah! Nicely done, high five.
Awesome!
See how the airflow from the board keeps the air surfer in the air? Well, the trick is to give it just the right amount of air to keep it in control. Not too fast and not too slow. That's the science to good tumblewing flying. So, with the points from the last round added up, Team Phil and Team Lisa are tied again.
You know what that means? Tiebreaker! Thanks very much for watching Science Max Experiments at Large Tumblewings. You want to go first
I
this
do,
time?
let's do it.
Okay, you go first this time, and then I'll follow you. I think it's easier to go first. So, okay, ready?
Yeah.
Ready, set, go.